Good afternoon or morning, maybe even evening. Today we're going to be looking at day 3 in unit 4 in calculus. Okay, so let me just open my Blackboard up here. So what we want to look at today is we're going to get into that second part of the second derivative test, part 2 on the second derivative test. So let me open this up first and let me move this over here. Okay, and as that's opening up, I'm just going to set up. Now, we're going to do a more complex question. So a typical question that you'll see in this section, okay? So talking about concavity, intervals of increase and decrease, critical points, inflection points, kind of combining everything that we did in the first couple of days of this unit. So we'll wait for our board to open here. I have a particular question that I'm going to ask here. It's a more complex graph, like a power of 4 graph. So it's much more complex than the cubes that we've been looking at presently. Okay, so there we are. Okay, so let's hide this and we'll get our marker, our typing set up first. Okay, so this is day 3 on unit 4 in calculus. And we're moving along pretty good. I'm pleased with everybody's work to this point. And what we're going to look at is we're looking at part 2 in the second derivative test. And basically, I'm only having one objective today. And what I want to do today with you guys is I want to show an example or two of basically using both derivative tests to analyze a curve. Oh, man. To analyze a curve. That's what we're going to do today. So we're going to basically just do a couple of examples. And I'm going to do a more complex example, one that has a few inflection points, 2 inflection points, and like 2 or 3 max and mins, so that we can see a more complex curve in our calculus. So let me just get my rough data set up on the other page here so that I can see it. There we are. Let's see here. And then tomorrow we'll probably do the practice part in it. Okay, so let's see. Not review and practice. First derivative test. Second derivative test. Okay, this is what I want. Okay. All right. So what are we going to do here? Maybe I'll type this one first. There we go. That's the one I want to start with right there. All right. So let's just do the simplest thing. Let's do an example. Okay, so let's say find for the following curve or graph, if you like, find. Okay, let's find, and let's label these out. Let's find first of all the critical numbers, and I'll kind of put these in chronicle or critical points, if you like. I'll put these in the chronicle order that you should probably do them in. Okay. The intervals of increase / decrease. Okay, that kind of comes off the first derivative test. Okay, then we roll into the second derivative test. The max and min values. Okay, some calculus books will call these local extrema. rather than max and mins. Don't get confused when you go on to post-secondary and they talk about local extreme. They're talking about max and min values of a graph. And by local, they mean local because they're bumps rather than, as we know, most of these graphs go to infinity. Okay, D, we'll say concavity, regions or intervals, I guess. We'll stick with intervals of concavity. Okay, and any inflection points. Inflection points. I can't spell it all. Been a problem my whole life. Right, inflection points. Okay, so I am going to go through this with a bit more of a complex example than what we had when we were doing cubic ones. So we'll do a power of 4 one. And we'll try to do one that works out fairly evenly, but maybe not. Let's make it a little bit messy, okay? So I'm going to pick one from the Your Turn text that I have here, that I use. Okay, and we're going to use this as our example. Let's say the curve is y equals, whoops, there we go. Y equals x to the fourth minus 54 x squared. Okay, so that's our original curve that we have. Okay, so the first thing that we have to do, and always the first thing that we should do, is do the first derivative test, okay? Now, the first derivative test is to take the derivative, equal it to 0, and those areas that it is 0 at are our critical numbers. Okay, so let's do the first derivative test first. So y prime is 4x cubed minus 108x. Okay. 4x cubed minus 2 times that is 108x. Okay, now what we have to do is we have to factor this out and equal the y prime to 0, so to finding the critical points. So 0 equals 4x cubed minus 108x. So we can take an x out of both and a 4 out of both. So we've got 4x as a common factor. That leaves us with x squared minus, and 4 times, what would that be? 4 into 10 is 2. Carry the 2 over, is 27. Okay, 4x squared. Okay, now you may think that you cannot factor this, but this is a difference of squares. Remember, any number that we can factor this as well. Okay, 4x. So this is going to be x minus the root of 27 times x plus the root of 27. Okay, root 27, can we reduce that down? Yes, we can take a 9 out of it to make it into 4x x. Okay, when we reduce this down, this becomes 3 root 3. Okay, and if you can't remember how to do root 27 down, oops, sorry, I put root 27 again. Whoops. 3 root 3. I'll just do it on the side here for you in a minute here. Three root 3. Okay, you could use a decimal there, but I dislike decimals, especially in calculus. But you could use a decimal. You could go root 27 and say that's 5 point whatever it is. But if you're doing root 27, how you reduce root 27? Okay, that's just root 27 is 3 times 3 times 3. So then if we bring a pair of 3's out front, it's 3 root 3. That's how we did that, if you're wondering. Or you could say if we do it on our calculator, right? If we go root 27. Okay, my calculator changes it into roots, but if we did it as a decimal, it's 5.2. Now, is it wrong for you to use decimals? No, it's not wrong. It's just not exact. Okay, so you could put a decimal in there if you wanted, that's fine, but it's just not exact. Okay, so that gives us three possible factors, as we can see, three critical points. Okay, so we have three critical points. We have, in our critical points, we'll go over to the side here so that there's more space to work with it. We have 4x can equal 0. Okay, or x minus 3 root 3 can equal 0. Or x plus 3 root 3 can equal 0. So this gives us a total of three critical point values for x. So in this case, we divide that by the 4. We have critical points at x equals 0. Okay, and at x equal positive 3 root 3. Okay, or if you like, 5 point, what did we have? 5.196, so we'll say 5.2. If you prefer the decimal for use on calculator, or x equal negative 3 root 3, or if you like a decimal, I know some people like decimals for whatever reason, 5.2 negative. So there are our critical points for x. There are actually three of them. Okay, now we could go back and plug them into here and figure out what the y value is, and then we can find the max and min values, but let's not do that for right now. Let's just do our areas of increase and decrease. Okay, so if we want to do areas of increase and decrease, or intervals of areas, it's not a good word, intervals of increase and decrease, we can do a sign analysis for these three factors. Okay, so for that, this is for A, our three critical points. Okay, B for areas of increase and decrease, if I draw my number line. Okay, I have my negative 5.2 or 3 root 3, my 0, and my positive 5.2 or 3 root 3. Okay, these ones here. So if we're doing each of these factors, there's actually four of them. There's 4x, there's x minus 3 root 3, and x plus 3 root 3. So this one's going to have a 0 at the 0 spot. So it's going to be negative and then positive after that. Okay, so this one here at 3 root 3, which is 5.2, it's going to be 0. So 3 root 3 minus 3 root 3 is 0. So it's going to be negative up to there. Then it's going to be positive after that. Okay, and then we've got a third one in this case. It's going to be 0 right here. It's going to be negative up there and positive after that. So if we do all three factors together to get our areas of increase and decrease, notice that we have 1, 2, 3, 4 sections that we're looking at. So all together, that would be the whole graph, okay, of our derivative, because we're looking at our derivative only. Remember, we're not looking at this one here. We're looking at y prime, which is this stuff down here, because we're looking at slope, and slope represents, will tell us our areas of increase and decrease. So that's why we're doing with slope. So all of them together here, we'll just go 4x times x minus 3 root 3 times x plus 3 root 3. Okay, if we do all, so we got negative, 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 negative times a negative times a negative. That gives us a negative right there. Okay, the second section here, we've got a negative times a negative times a positive. Negative times a negative is positive times another positive is a positive. Okay, then over here in this section, we've got positive times a negative times a positive. That's a negative. Positive times a positive times a positive, that's positive. So we can see that we have here areas or intervals of increase and decrease. Let's move that up. There we go. All right, so we've got, okay, let's do our decrease first. So interval of decrease. Now you'll sometimes see me write it like this. Instead of putting the word decrease, I'll put a down arrow. Okay, that's going to be from negative infinity to negative 5.2. I'm going to go ahead and use the decimals here because that's what most students do. You can use roots though too as well. Okay, and also from 0 to positive 5.2. Okay, there's our areas of increase, or sorry, decrease, pardon me, decrease. Okay, this one here and this one here. Okay, our interval of increase, okay, from negative 5.2 out to 0. And then from positive 5.2 to infinity. Okay, so we've got our area intervals of increase and decrease. So that was B, using the sign analysis. Now we can do the max and min values just looking at this. Okay, so here we've got, at this critical point, we have a negative, a flat, and a positive. At this one, we have a positive, a flat, and a negative. And at this one, we have a negative, a flat, and then a positive. So this is a min, this is a max, this is a min. Now, we can plug these numbers in to get the y point, to get our maximum and min values, and we can see the value of the number as well. So we could either plug the numbers in or state that there's or use this technique here. So there's a minimum at x equals negative 5.2 and x equals positive 5.2. Now we could check that using the second derivative test as well if we wanted to, right? There's lots of ways we can do this. Okay, and then we have a maximum at x equals 0. Okay, now if we want, we could see, well, that might be an inflection point there. Okay, so this might actually be an inflection point as well, depending on that situation there, but it might be a local maximum. So if that ends up being an inflection point when we check E, we'll have to knock it off our list. Okay, so we'll just possibly it can be that way. So D is to look at the concavity. This is where we can use a second derivative test. So now we have to do the second derivative test. So we have to take 4x cubed minus 108x and do the second derivative. So let's say y prime was 4x cubed minus 108x. Okay, just to make sure I'll get that right there. Okay, didn't. Okay, so then we're going to do y prime prime. All right, so this gives us 12x squared minus 108. Okay, so now if we wanted to check to see if these are max mins, if we put a 0 in for x there, we're going to get, this is an easy way to check with the second derivative. If we put a 0 in for x there, we get negative 108. So that indeed is a maximum. So we're good. If we put negative 5.2 in for for x, you should get a positive number here. So let's just try that. So if we go 5.2 squared, that's 27.04 times 12. I get 324 points, whatever. So if I minus 108 from that, that's a positive number. So that indeed are summarizals of these two things here. These are all correct. Okay, so this will give us our inflection point and our area of concavity if we solve for it. So let's go ahead and divide everything by 12. So if we are going to set this to 0 to get our inflection points. Set it to 0. Okay, so there's a couple things we can do here now. We could take out a 12 and eliminate it and then factor, or we could just move and factor it out, or we could just move the 108 over. There's two ways to solve this particular one. 108 equals 12x squared. Okay, 108, 12 times 9 is 108, so we divide 12 on both sides. And we get x squared is equal to 9. Okay, got to be careful here. Square root of 9, to get square root both sides, square root of 9 is plus or minus 3. So x equals plus or minus 3. So we have an inflection point at x equals plus 3 and x equals minus 3. So there's two inflection points there. Now we can obviously find those points by plugging them back into the original if we wanted to do the graph and everything like that. But there are two inflection points at x equal. If I want the specific point, I have to go all the way back to here and plug our numbers in, okay, which we might do. So that, and then we'll look at the area of concavity. Oh, I did inflection point first before I did D. So we'll do D and E together here. Okay, so those are the inflection points. Now, how do I get the area of concavity? I look at the second derivative, and I look where it is positive and where it is negative to see if it's concave up or concave down. So we do another sign analysis, but we look at the inflection points of 3 and negative 3. Okay, because those are the areas where the concavity changes. So we have at I guess this, we should if we're going to do the factors here, this would have been 12 times x squared minus 9, right? Then if we cancel the 12 out, 0 equals x squared minus 9. So we have two factors here, x plus 3 and x minus 3. Okay, if we do this one here, okay, so we have an x plus and an x minus 3. So the plus 3, obviously, everything here is negative. It's 0 there, positive here.
History.
Yep.
Badminton practices are on Wednesdays, right?
Yep.
What times again?
Right after school till 5.
5.
Yeah. You got work to do again?
Yeah, but I always do it. Just go. So the legend goes, don't forget.
Okay, no worries. Okay, so now if we do the whole point here of these two together, okay, or that whole concavity part, x minus 3 and x plus 3, you're like, well, what happened to the 12? Well, you can eliminate the 12 because when we divide it on both sides, 0 divided by 12 is still 0, right? So we've got a negative here, a positive here, and a negative here. So this is our concavity intervals. So it's concave up from negative 3 to positive 3. And it's concave down from negative infinity to negative 3, and from positive 3 to infinity. Okay, So that would answer all 5 questions. So now the only thing that I would mention to you is I'm only putting the x points in this question. They might want the y values. If they say, what is the inflection point? Say it's at x equal 1, but what's the y value? So you might have to go in and plug these numbers in to get your y values. So if we wanted to do that for critical points, we could take our calculator out, go back to this original question, and this is where we're plugging it in, into x to the 4th minus 54x squared. So if we plug in a 0, we have a critical point at 0 and 0. There's our first one. Okay, 0 and 0. So get a 0 for y. Now let's do 5.2. We'll use 5.2 because it'll be easier with our calculator. So go 5.2 to the power of 4 minus, let's do that again. 5.2, sorry guys. 5.2 to the power of 4. Okay. Okay, minus 54 times 5.2 squared. Okay, I get about 729 negative. So this one would be, what was it, 5.2 and negative 729. It's not quite that. We're doing approximations. And then the last one would be negative 5.2. And what would we get here? It's probably the same thing, actually. Yes, it is. This one is also the same thing, approximately negative 729. Okay, so there's our 3 critical points with the y values in them. Same idea here for our inflection points. We could put the 3's in. Okay, so our 2 inflection points would be 3. And if we go, what was our original equation there? Let's put in 3 here. So 3 to the power of 4. Okay, that's 81 minus 54 times 3 squared, which is 9. So we'll get 405. Okay. So if they want those extra ones there, so our 2 inflection points, if we want the y points on them, 3 and negative 405, and negative 3. And is that one going to give us, yeah, it's going to be, they're both even, so it'll be the same. Okay, and that's how you do a more complex question. So that's a good half hour there and doing those things. So I'm going to stop there today. I'm going to open up the practice in the second derivative tests that have questions like this and the other ones that we did last day. And I'm going to give you all of tomorrow's class to work on that as practice, and whatever you have left today, if you want to get started on it or if you want to just take a break and do it tomorrow, that's really up to you. But I'll open that up for you, and you can do some practice with the second derivative test. And then we only have one thing left, and that's how do we put all this information together to get our graph sketch? Basically taking all this information that we have here, that we've figured out, putting our dots on our page or our graph, and finding the general shape of our graph. Okay, and that's what we'll do next day after we do the practice. Okay, so we'll see you tomorrow.